Okay, Algebra 2 people, here is the video for your logarithm practice exam. So number 1, we're doing our graphing. So with an exponential, it's easy to plug in values. 1/2 to the -1 is 2, 1/2 to the 0 is 1, 1/2 to the 1 is a 1/2. So you can easily plot those points to get an idea of what your graph would look like. I do want to see you mark up your asymptote, which is going to be this x-axis, so make sure you don't cross that. And then your graph should come down and approach it, but not touch. And on this one, so you have already clearly labeled a point by filling out the table. On the other hand, with the logarithm, you're not going to get a nice value to graph because there'll be decimals. So think about what your normal parent graph would be. The parent graph would have an asymptote here and cross at 1, 0. And so what this x plus 4 does is it moves everything back 4 places. So we are going to erase this, and whoa, that was weird. And then we're going to graph the result of moving back by 4 units. So 1, 2, 3, 4, your asymptote will be here at x equals -4, and the point that was at 1, 0 is going to move back to -3, 0. And that's kind of a high graph there. This is just a sketch. So -3, 0 is where you're going to cross. So you want to make sure you give me that 1 point and make sure you label your asymptotes. Okay, number 3, this was supposed to say 3/2, so it was a bit of a typo, but the same idea, we can still write it as an exponential, so you pick up your base, go to the other side of the equal sign because logs solve for the unknown exponent, and set that equal. So this will be 16 to the 2/3 equals n. If it had been 3/2, you could have calculated it without a, you could have figured it out without a calculator. This one you really have to enter it on your calculator. So on the actual test, there won't be any decimals on this part. Okay, so evaluating this log, well, remember that we have this property that says I can take an exponent and move it in front. So what I really have here is 15 times log base 9 of 9, and this is the same thing as 1, so we have 15 times 1, which is 15. It's another reason why these just cancel, and your answer is 15. Okay, so now we're doing the estimation, which you'll at least have the calculator to work with your decimals, but I want to see the expansion property that you use. And remember, you always want to immediately write down, since these are base 2, write down log base 2 of 2, because that equals 1, and you might want that as a clue for some of them. So this first one, notice your argument is being divided. So we're going to expand this as log base 2 of 7 minus log base 2 of 5. And then you substitute in your decimals. So this is 2.8074 minus 2.3219. And you are allowed at that point to enter that on your calculator, 0.4855. But I do want to see the expansion. So log base 2 of 49, I'll write that one out here, is log base 2 7 squared. And we can take this 2 and move it out in front. So 2 times log base 2 of 7 is like taking the decimal 2.8074 and multiplying it by 2. And that is going to give you 5.6148. Then the last one we have here is log base 2, 10. We can get 10 from 2 times 5. And since that's multiplication, we can expand it as log base 2 of 2 plus log base 2. Notice that when you expand, you end up with 2 logs versus when you condense, you only have the 1. So now this is 1 plus 2.3219. That's the same thing as a 3. Let's see if I can get this. There we go. So let's rewrite that. That was going to be a 3.3219. There we go. Okay. All right, so use the properties to expand. So notice that we have a fraction. So this symbol here, think of it as subtraction. So division and subtraction go together. So the first thing we're going to do is break this up into log 8x minus log y cubed. But to be as simple as possible and as expanded as possible, you shouldn't have anything more than one term as your argument. So we still have a product here. So when I can expand this as log 8 plus log x, because multiplication and addition go together. And over here, all I'm going to do is take this 3 and move it in front. So I have minus 3 log y. So log 8 plus log x minus 3 log y. And notice you have a very simple argument for each one. That means you've expanded it as far as you can. Okay, condensing, in the end we're only going to have 1 log. Okay, so the first thing you have to do always before you can start condensing is move these coefficients out of the way. So they have to go back up as exponents. So the first thing we're going to have is the log 6 plus log 3 squared, which is 9, minus log 4 to the 1/2 is like square root of 4, so that'll be a log 2. And then start at the beginning and work with the first 2 terms. So this is addition, which means this condenses into 1 log, and addition goes into multiplication. So 6 times 9, which is 54, and we still have minus log 2. Now that is then going to condense into 1 log, and because it's now subtraction between them, we're going to divide the argument. So this simplifies out to 1 log, 54 divided by 2, which is 27. Okay, so just do them one step at a time. Now this one expressed log base 18 of 4 in terms of a common log, which in other words means base 10. So you could write this as log, remember the bigger number goes up high, smaller number goes down below, and since we're writing it with a base 10, we can then just put in here base 10. Now be really careful about where you're putting your numbers. The base is a subscript, but the 4 should be on the same line as the log. It shouldn't look like an exponent. And actually, you don't even really need to write the 10 because it's already assumed when it's not there. So I'd accept either one of those. Okay. Now on to solving. So again, when you're solving an equation, you're always using inverse operations. The inverse of a log is an exponential. The inverse of an exponential is a log. So we're going to start off here, though, with the same base, because notice 4 and 16 share something. So I'm going to rewrite this as 4 to the 2x minus 12 equals 4 squared. And since I have the same base, I can cancel. So 2x minus 12 equals 2. 2x equals 14. So we get that x equals 7. Now, let's say you totally didn't catch that they have the same base. And you're like, okay, it's an exponential, so we're going to write it as a log. Well, look what happens. You're going to have a log. If I rewrote that as a log, that would be log base 4 of 16 equals 2x minus 12. But hopefully you realize log base 4 of 16, this is just 2, because 4 squared is 16. And then you would go on and you'd get the same answer. But you shouldn't have the log in your answer. You should be able to evaluate it. Okay? So now we have a log equals a number. So the inverse operation is exponential. So we're going to start with our base. You always go raise it to the exponent, set it equal to the argument. So 2 to the 5th equals 3x minus 7. And so 2 to the 5th is 32. And so then we can add 7 to both sides. So we get 39 equals 3x. And x, equals 13. Okay, go on to the next. So now as we get into more solving of problems, we notice we have a log minus a log equals a number. So you can never have that. You need to only have one log equals one number. So we are going to have to do some condensing. Condense into just one log equation. So how do I condense this? Well, you have subtraction. Subtraction goes with division. So you have one log of the same base, 2. On top is going to be 4x plus 12 divided by the other argument, x, and that equals 4. So now we have one log equals a number. So what is the inverse of a log is an exponential. So we're going to pick up our base. That picks up the exponent and set it equal to the argument. So we have 2 to the 4th equals 4x plus 12 over x, and now what you have is a proportion, so we can cross multiply. So we end up with 4x plus 12 equals, so 2 to the 4th is 16, and then go through and solve. So I have 12 equals 12x, so we have that x equals 1, and that answer's okay. Doesn't make our argument negative. All right. Okay, so now we have a natural log equals 3. So again, we still want to have the inverse, which would be an exponential, but now the base of a natural log, remember, is e. So there's a little shortcut you can do. We can just e both sides, and remember, e and ln always cancel, so I end up with x minus 2 equals e cubed, and then all I have to do is add 2 to both sides, and there's your answer. So x equals e cubed plus 2. So I'd rather you just give me exact answers than decimals, so go as far as you would right before you would enter it into the calculator. That way, just in case you enter something wrong, I actually get a more accurate answer. Okay, so now we have the easiest ones. You have a natural log equals a natural log. So since it's the same base on both sides, we just cancel them out. It's kind of like raising both sides to the e, really, and the e and the ln's cancel. And so all you have to do is solve 2x plus 8 equals 4x minus 6. So 2x equals 14, and we get x equals 7. Okay? So now on number 16. So these ones seem to be more of a problem for some people. So you have an exponential. Well, the inverse of an exponential is a logarithm. So we're going to rewrite this as a log. So how does that look? That means we're going to write the word log. Our base is the 8. So here's the base. So you go to the other side of the equal sign of 40 is going to equal the unknown exponent, because that's what logs do. Now, log base 840 is not something that you would be able to enter into your calculator because they only understand either natural log or base 10, the common log. So we're going to rewrite log base 840 using our change of base formula. So that's going to be log 40 on top, and the lower number goes on bottom. That equals 2x, and since we're trying to solve or isolate x, we're going to divide both sides by 2, or you can think of it as multiplying by half. And as far as I'm concerned, just leave your answer like that. So 1/2 times log 40 over log 8. And that would be an exact answer. Okay? All right, so now we are actually finding the inverse again. You've been doing this really. Every time you solve one of these problems, you are doing the inverse. So now we're going to change our x and our y. And since this is a log, the inverse of a log is an exponential. So we find our base, which is 5, pick up the x, and set it equal to y minus 4. And since we want to isolate y, we'll have 5x plus 4. And instead of y now, we're going to use our inverse notation. So f inverse of x equals 5 to the x plus 4. All right. Okay, so now a little multiple choice. So here is a transformed exponential. This -1 right here, we know it's outside of everything, so it's going to drop your graph down 1 unit. So that right there kind of narrows it down to here, but let's just double check. X plus 3, remember, moves you in the opposite direction, so it's going to move you to the left. So that tells you it's going to be C. All right. Okay, so these are the only 2 problems where you really need a calculator, and you are going to want to give decimal answers as well as show your work. So we have the function p equals 12, e to the kt models a population in millions of a particular country for t years after 2010. So this is kind of like our t equals 0 when we're starting to count the population. A recent change in the economy has made the k value, the rate, 0.22, okay, and you're going to write the function. So you're just going to put all the pieces together. So p equals 12 e to the 0.22t. Tell whether your function represents exponential growth or exponential decay. So remember, e is about 2.7, and since your exponent is positive, this is going to be growth. So the population is growing. Estimate the population in 2018, so that's like saying when t equals 8 years later, and round it to the nearest million. So what we're actually calculating is 12e raised to the 0.22 times 8. And so that's just something you're going to want to enter on your calculator. You should have an actual E button, and that should give you 69.75, and since they want it rounded to the nearest million, that would be about 70 million. Okay. All right, now we're looking at something that is appreciating. That means it's growing in value as opposed to depreciating. That's why we're going to use an equation that has a plus here. It is originally valued, so its initial amount, it's kind of like the same thing as what do you initially put in the bank. So this is our P value, 75,000. Our R is going to be, remember, make it a decimal, 0.045, because that's how much it's appreciating each year. And we want to know after how many years, in other words, solve for T when it equals, and this will be the A value, 79,000. So we're going to set up our equation, 79,000. Well, when will that equal? So we have our 75,000, 1 plus 0.045 raised to the T, and that's what we're trying to solve for. So we're going to simplify this out. First, let's go ahead and get rid of this 75,000. So we divide both sides. All these zeros will cancel. So 79. And if you want to make that into a decimal, that's fine. I don't have a calculator with me right now. 1.045 to the t. So notice you are trying to solve an exponential problem. Well, what is the inverse operation of an exponential? It's a log. So that means we're going to write this as a logarithm. So log, the base is 1.045, and of the argument, which is 7975, that equals the unknown exponent. Okay? Now, I actually would like to see you use the change of base because that's what you're going to have to enter into your calculator. So what you're going to have to enter into your calculator is a log 79, and again, if you made this into a 1 decimal, that's fine. All of that divided by log 1.045. That will give you the time, and that should give you 1.18 years. So remember, it's not just about the answer. I'm also going to be looking at the work, so I do want to see what it is that you are entering into the calculator. All right, hope that helps.